The next part we're going to talk about is profiler-guided optimization. And this combines what we've just talked about, the idea of profiling, with something that we talked about a little bit earlier, the idea of self-optimizing software. In 2015, we were fortunate enough to have a guest lecture from somebody at Microsoft who was knowledgeable about this subject, actually in the room to give a guest lecture. And in subsequent years, I was not particularly able to convince him to drop in just for the lecture. Now there's a pandemic, so that wasn't happening. And what classroom? What lecture? Here we are. So let's talk about this subject. Our discussion here is not actually limited to Rust, although we'll use Rust for some examples in it, just to give you some idea about some of the things that we could do with profiler-guided optimization. You will remember that when we talk about the compiler, it will, using static analysis, make its best predictions about runtime behavior, such as your typical branch prediction. If it thinks A is less than B, it will compile and guess that it is, which is more likely, is A is less than B, and therefore it will order instructions and generally conduct itself in such a way as though that were true, recognizing that if we're wrong, there could be a branch mispredict, which will not be the end of the world. It is just going to be less ideal in terms of actual performance of the application. Fine. As we know, the compiler looks at that and asks whether it thinks it's more likely. Because we don't have a specific guidance about this, if there's no other information available to us, then we'll probably fall back on some rule which says, the fallback rule is, the first case in the if branch is usually the one that's correct. That works, but if we're wrong, then our prediction is wrong, right? Maybe our prediction is wrong. We get it wrong 5% of the time if our prediction is right, and we get it wrong 95% of the time if our prediction is wrong. But the only way that we actually know that is to run the program. Then we have a similar thing for the previous code. We have trait polite, which has a function greet, and we have struct kenobi and grievous, and then implementation of polite says return string from hello there and return general kenobi, and then virtualization, the devirtualization function here takes a thing which is a reference to something that implements the trait polite, and then it does thing.greet. If we don't know whether a normal expected value here is there's going to be much more Kenobi than there is Grievous, I'm just saying, one of them appeared in more movies, then the compiler can't do the devirtualization, that is, replace the call with a virtual call with a real one, and if in fact there was exactly one type that implemented polite, we wouldn't have to guess, but the compiler will guess and say, I think it's most likely going to be of type Kenobi, and I could be wrong. If I'm wrong, again, there's basically a branch misprediction penalty for getting it done, but we'll find out. We'll find out. And the third thing, which is really the same thing, just dressed up differently, is the match statement. The match statement, or the switch statement in C language, or other language that uses that as its version, is going to be the same thing. There is a prediction, and our prediction could be right, it could be wrong. What is its typical value? If we know that x is likely to be between 0 and 10, we could assume that, and that would be the thing that we predict. In a match block, could you rank them in order of what you think makes the most sense? I mean, you could. Do you know which ones they are? And why should you have to do it by hand? There does exist a solution to this, and we've talked about a few of them already. One of them is we could provide hints, where we could say, I think this is likely, or I think that's unlikely. We've covered already the idea that hints are not always a good idea, even if you're pretty sure you're right. Number two, we've said, well, the Java Hotspot virtual machine updates its predictions on the fly, and if the initial prediction is wrong, the just-in-time compiler notices that, and it adjusts accordingly. That's neat. I suspect the .NET runtime does the same thing for something like C#, and we've already covered it's Rust, and we don't have that option. And having the program change itself at runtime, as we've seen, is somewhat complicated and somewhat difficult. So if we don't do that, the compiler runs, it does its job, and that's it, and the program is never updated with any newer predictions if more data becomes known. And the objective of POGO is to, as Profiler Guided Optimization is sometimes abbreviated, is take data from actual runs of the program and use that to inform the predictions. In some cases, like I said, this would be covered in self-optimizing software. If it's an if-else condition, if it turns out our prediction is wrong, there's only one other option. But in the match case, it could be hard because are you going to compile 100 different versions for every possible value? Maybe not. Maybe that doesn't make sense, or maybe having dynamic code generation for whichever one is the one you want to do is impractical or impossible. But profiling gives you the options to have these things determined at compile time based on observed actual data, and therefore hopefully give good results. That means, of course, your program to produce the final executable has really a multi-step compilation. First one is you compile with profiling enabled, and then you do some runs to collect some data, and then recompile the program, taking as input the profiling data to produce a more optimal executable. We'll expand on all three steps. All right, so first one is measure. And measure is generate an executable with instrumentation. As we've seen with profiling before, sometimes you want to take notes about whether a branch was taken, whether a function was called, all those things. So we're generating it, and it results in a file, once it's compiled, that has these probes that record data. So when we enter a function, write it down. When function A calls function B, write it down. Value probes. At the time when we evaluated the match statement, X was 21. Okay, that kind of thing is all noted. It is kept on file, kept on hand. We want that information. We need that information. It makes it possible for us to do predictions later, and that is important. It's something that we need. So that's what we do, and the result is we get a compiled version. The compiled version has the executable with the instrumentation in, and on top of that, we end up with an empty database file. This database file is where we are going to record any of the observations that we have. When we have an observation that is, something is tripped, it's a function entry probe, it is an edge probe, it is a value probe, anything like that, then we write it down and it goes into that database file. Very good. That's the way we do it. Step 2, training day. Training day. So when we've actually got our system set up, our function entry probes are there to count how many times a particular function is called. The edge probe counts transitions. The value probes give a histogram of values, so most of the time it's this, and other times it's that. All those things remain, and when the phase is ready for phase 2, it's training day. Run the instrumented executable through real-world scenarios. Ideally, you spend the training time on performance-critical sections, and you are focused on the ones that matter the most in your program. Real-world scenarios are the best. Having this run on your unit tests isn't ideal because it's not doing what you need. It's not doing what you want. You should be testing out based on what you expect people are actually going to do, and the things that are most important in your program. You don't have to do this in a single training run. You can use many training runs. In fact, the more training runs you have, the more data that you have collected. And the more data you have, the better decisions the compiler will be able to make. Okay. Now, the other thing to remember is don't execute every single part of the program. This is not software testing. Your goal is not to try everything as it should be. The goal is to focus on what's important, because you would be counterproductive if you didn't focus, and if you did just try everything equally. You're teaching the profiler at that point, you're teaching the compiler that everything is important, which is the same as teaching it that nothing is important, right? You don't want to misinform the compiler about what makes sense, otherwise you don't get good outcomes. If you ask me about what's on the exam, if I just tell you everything's on the exam, you're probably thinking that was an unhelpful answer. You probably want me to be more specific. You want me to give details and not just say yep, everything, definitely everything. It's very helpful, right? The answer you gave me was perfectly true and perfectly useless, right? That's how that works. All right, once that's done, you compile the program again. When you have everything that you need, then you can run it, and you run it, and you hope that the output of the compiler is a better version of the executable than you would have had before. Right? We hope. All right, so to put it in a summary graphic here, here's the steps. So we compile and we get the instrumented executable. We run it one or more times. We get a dynamic file. Now, the thing is that usually the data that we've got are not quite 100% usable in their immediate format. You might actually need to post-process them a little bit before it's time to happen. And, well, for that, the tool for this is llvm-prof data. And it organizes what was originally a .prof raw file into a .prof data file. And you can merge multiple runs into one using this tool. And then once you've done the recompile using this prof data, you get your optimized application. It's not necessary to do all steps for every build. You can reuse your training data while it's still valid, so not every tiny change has to actually get it. The recommended workflow for doing something like this is, if you are the developer A who is performing the steps, you check the training data into source control, and then the whole other members of the team can use that and take advantage of the profiling data that has already been generated, thus preventing you from having to do it yourself again, right? And when you need to update it, because it's in version control, anybody can update it. That's cool too. Okay, what does it mean actually for it to be better? We're talking about how you actually do it. We've looked at an example about how to predict branches, for example, and obviously we can imagine that predicting it correctly is faster than predicting it incorrectly. But there's also other things that we could do in terms of compilation that have to do with what choices the compiler will make. And so the compiler will take the data that it has and aim for speed in areas that are hot, that is to say ones that execute a lot, performance critical, or common scenarios, and will also alternatively aim to minimize the size of the code that's generated in areas that are cold, that is to say not used very often. And we estimate that something like under 5% of the methods should be optimized for speed. You can't optimize everything for speed, otherwise it stops being effective. You're not getting the outcome that you want. All right. as we've said before, we can combine multiple training runs and also manually give some suggestions about what we think is important, and that's allowed. You can also give weightings to different training runs, which will also help with indicating to the compiler what you want and what you think is important. And absent that, the more scenario runs there are on a training data, the more this code executes, the more important the compiler thinks it is likely to be. So here is a full test scenario done in Rust using the command line tools. So we will use Rust C with the -C profile generate and then a destination for where we want the profiling data to go, and compile and run main.rs. Then we'll run the binary a few times with a few things, and they will generate prof raw files in our temporary directory that we have suggested. So we're going to run the main program with input of mydata1.csv, then 2, then 3, and we'll use LLVM prof data merge to produce the merged data, and then we can compile it with C profile use equals and then the file that we just created. And all the Rust C files have to be compiled. All the flags have to be the same. Otherwise, we don't compare apples to apples, and that's not going to work. All right. Behind the scenes. So in the optimize phase, the training data is used to do the following optimizations, which, full disclosure, are the kind of things that I talked about in the previous edition of the course as being C and C++, and I can't promise with certainty that these things exactly happen when we are doing it for Rust. However, there is full and partial inlining, function layout, speed and size decisions, basic block layout, code separation, virtual call speculation, switch expansion, data separation, loop unrolling. Okay, long list. For the most part, I don't have to recap what was covered here because we've talked about all those things to a greater or lesser extent. We've talked about inlining at this point almost to death, so I don't have to talk about it either. Function layout has to do with where are functions. Again, nothing too new or exciting for me to tell you about there. Speed and size decision we have just covered, so that one's new, as in, we didn't talk about it before today, but it is no longer anything really we have to talk about anymore because we've covered that. Basic block layout and code separation, those ones are new as well, and those are the things that have to do with how data and how functions are packed in the binary, right? When we're generating the binary code, you can arrange things almost any way you want. I don't think there's like a strong reason that says anything has to execute from top to bottom, although that might be more efficient and it might be better in terms of predicting what's supposed to happen, but I don't think there's any law that requires it. And ultimately, choosing how to pack the binary, it makes sense. And virtual call speculation, again, we introduced the topic previously and we've covered it again here. Switch expansion has also been covered. Data separation and loop unrolling also covered previously. Data separation we talked about in false sharing, and loop unrolling has been covered in compiler optimizations. So that's what it does. Those are the decisions. Like I said, most of them are not new to us. They're not strange. They're not unusual. They are just things that we have already talked about, and all that's different here is using the runtime data to make a decision about whether it is something we want to do or not. According to the linked source in the notes, most of the performance gains come from the inlining decisions, and decisions about what to inline are based on the call graph and the profiling thereof. The decisions, though, are kind of broken down a little bit, not just at a function level where you say, okay, this function is definitely always inlined, but actually takes some more context into consideration. And here, for example, are the relationships between functions. We have a bunch of functions with random names that sound like baby talk. But we can see that function baz is always called from bar, and it's called 140 times, and we'll say that's a lot. So you might expect that the decision would be to inline baz into bar. However, with POGO, what it actually does is think about it a little bit differently. It thinks about it with more context, so it makes decisions about whether to inline something based more on a wider picture. That being the case, then this would be a representative decision for how the compiler with the profiling data would choose to inline data, right? It would see, there aren't too many calls between, say, bar and baz if we started at bat, and it would say, actually, it makes more sense to inline bar into bat in that case. And you don't get exactly the same thing that you would expect, but that's okay. The additional context allows it to make different decisions depending on whether something gets called from A or B, and ultimately that is going to be a win for your program, because you inline where it makes sense and you don't inline where it doesn't make sense, and choose accordingly. Okay, so yeah, the other thing that's noteworthy about this is that packing the blocks is based on call graph profiling. That is to say, functions that call each other tend to be located near each other and put successors after their predecessors. The idea is that if you pack the related code correctly, it reduces the chance of cache misses, right? If you call a function and the callee is in the same function, same page as the caller, that means that we have no cache miss possibility because that page is already in cache. In which case, that is page locality, and that's the goal. That's the dream. It won't always be that way. If you can make it in the next page, that would be all right. Again, not necessarily the dream, because the dream would be having it be in the same one, but our second best option would have it be in the next one, because that means that, it is predictable, right? One of the things that matters about making your cache usage efficient is making it predictable. And if you can make it predictable and say, okay, so we are proceeding from one to the other, that would be of benefit. So, yeah, that's the goal. And so if your call graph looks like the thing on the left, where A calls B and B calls D, but A also calls C and calls D, the optimized layout would put A, B, and D together because there's more calls between them, and the C stuff happens somewhat more rarely, and that would be okay. So according to the author in the page that I'm looking at, it says dead code goes in its own special block. I don't think it means truly dead code as in the sense that it's compile time unreachable, because in that case the compiler will probably either not compile it or will give you an error and say this is unreachable code and you should delete it. But I think what it actually means is code that never gets invoked in any of the training runs at all. And so that's great. We've summed up to some degree what we do. Here's the training data. It tells us, do we do this? Do we do that? What does the compiler do? Does it work? Well, here's an example. This is an application under test. This is a C test suite spec 2K, which is one of those artificial type tests, but that's okay. The goal is to make a determination about whether POGO works. Whether it works for your individual program or not depends a lot on your actual program. We hope the answer is yes, and we'll find out in real life if you ever take it for a spin. But for Spec 2K, given the different apps, we can see that there is a speed gain in all of them, from relatively small 6.6%, which, don't get me wrong, I wouldn't say no to. Would you like 6.6% more money in your bank account? Okay. On the other hand, could it be 36.9%? I'd rather have that. So these are of course synthetic benchmarks, so they're not exactly like what you do in the real world, but you can speculate at least a little bit about how well they translate into real-world application performance. But it's encouraging to see at least that they don't ever get worse. So that suggests that profiler guided optimization, although it does take some extra work to do it, does seem to be worth doing.